New screen recording. Now, this is one moment in time. One moment in time. So we have in our possession, oh my goodness gracious me. Where did it go? You guys, moment in time. This is our background music as we proceed to the next section here. There she is, Whitney in her prime, 1989. Now, what's important about this video is that actually Whitney was an accomplished mathematician. And Whitney had in her, you'll see in this video, it writes up actually all this about being the slope of a tangent line being different than the slope of a secant line, because she's talking about one moment in time, not the average rate of change over 2 periods of time and getting a general sense. She really talks about one moment in time. Okay? Now, here you go. It's a little, I'm going to scoot ahead because she talks a little bit, so we don't need to see that. Here it is. That right, okay, right there, see that right there? That is the slope of a secant line is the average rate of change. Sorry, I got to translate this for you as it goes. Okay, wait, here goes the next part. Right, so you see this x minus h? We're going to talk about that x minus h as the slope of a secant. We're going to, versus the instantaneous rate of change at one moment in time. I will write this in English later, but I don't have time. I'm just going to orally translate what that says later. Okay? There. Oh, sorry, you'll just read for yourselves, those of you who know the language. Okay, we're going to use that as background music. More importantly, let's get on to the mathematics. There we go. Good job, Whitney. So let's do subtle. When she gets to the chorus, I will pick up the volume, I promise. You hear that? One moment in time? Yeah. When I was more than I thought I could be? Right. We're going to be more than just a secant. We're going to get into derivative calculus. More than we thought we could be. A heartbeat away means that line, we actually get closer and closer with a secant to being just a heartbeat away from a tangent line. I'll talk about that in a minute. Okay, average rate of change versus instantaneous rate of velocity. I want to do one more analogy. Here's a ball. Rolls 16 feet in 4 seconds. If you draw this picture with me, I love how it talks about destiny in mathematics. That has a lot to do with life in general. Okay. Time. Seconds. Here it is. Eternity. So eternity, we're going to talk about limits to infinity. She's talking about to eternity, a limit as things approach infinity, and that's really at the heart of this tangent line stuff. Whitney was really pretty amazing about her comprehension of general physics properties as well. Okay. Feet. 16 feet in 4 seconds. You all following me? Look at that. Now, to go 16 feet in 4 seconds, Ryan Ingram might think that the ball did this. Whoa, right? But Ryan Ingram's ball travel is still 16 feet in 4 seconds. Ryan Ingram's average rate of change is still 4 feet per second on average. 4 feet per second. Right? Ryan Ingram's. Now, Jackson Lynch, he rolls his ball, and look what his does. Whoa. 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 Right there, see how that is? That's Jackson's roll of the ball. 4 feet per second. Average rate of change. That's what these are. These are average rates of change. Now, the key is, what that means is you are connecting a secant between where you start and where you end. The 4 feet per second is that slope of that secant line, that average rate of change that goes on there. A lot of weird things can happen with the instantaneous rates of change along the way. If I go to 3 seconds, you sing it, Whitney. Wow, she's really picking it up there. Whoa. Whew. Man, sorry, that just kind of gets you. It's emotional. Now, Now I'm going to go to 3 seconds. You see the notes? I can't make my pen work. 3 seconds. Check out the instantaneous rate of change at 3 seconds for Jackson. Jackson, your instantaneous rate of change seems downhill. Now check this out. Do you see that instantaneous rate of change is at that moment? Do you see Jackson's speed? Now let's go back to Mr. Seeley's trip. Do you guys remember Mr. Seeley's trip? Danny, you got to remember Mr. Seeley's trip and jot some things down. Remember today's Master of Calculus Day. You got to be. What I have right there is a moment in time, the speed. Jackson's got a downhill slope in his instantaneous rate of change. Let's say it's my trip to Des Moines from Minneapolis. So check this out. What does it mean when I get to Lakeville and then it starts going back like this? What's it mean when Jackson goes back like that? What's that dip all about? Turn around. What happens when you're leaving Minneapolis? You get to Lakeville and you come back a few miles because you want to go to Fleet Farm on the northern side of Lakeville because you want to get a couple things for the trip. So we go back a few blocks to Fleet Farm, shop for just a second. You get back in the car, you go at, now look at this speed right here. You see that vertical speed right there? We go many miles in 0 period of time. That would be the time warp button in the minivan. See that vertical part right there? That's a speed of many miles in 0 seconds. That's like a wormhole. You just travel like this, okay? So it travels really fast. Very steep. Did you guys know that steeper means faster? Steeper is faster. Oh dear, my pen's fidgeting. That is not me, I promise. It's my pen. Steeper's faster. And vertical like that, that's like undescribable super speed because I went many miles in a 0 period of time. Isn't that crazy? Now Jackson got up here, he came back. What is Jackson doing? Where is he going now? What happens if this is the ball rolling 16 feet in 4 seconds? What does it mean to go back like this, Jackson? What would you say your ball is doing?
Rolling back.
Rolling back. Kind of heading back in your direction towards you. Now, what I'm describing here is feet from a start location. And Abe, it sounds like you're going to say something really important here. Go for it. Yes, Abe, you may use the restroom. This little thing we're talking about is displacement. You guys are seeing what displacement describes how far you are from a starting location. Displacement is like, I don't know, I started in one location, I ended up 16 feet away. Sometimes it goes forward and sometimes it came back. You guys ever seen the movie Ferris Bueller's Day Off?
Yeah.
What was the displacement of the car at the end of when they finished their big day out and they got back home? It's in the garage again.
What happened?
They put the car back perfectly, right? Displacement was 0.
But didn't it fall?
But the problem was the distance they traveled, the odometer. What was on the odometer? We don't know, but whatever they did, they put it in reverse and tried to reverse the odometer because they realized that they had gone a long ways. In the process, somebody took off with the car. Oh, you got to see that movie. That's great. Displacement is from your start. So that's like a place like how far you displaced yourself versus distance traveled. That's your odometer reading. That's like mileage you put on your car. That's a little bit different idea. Okay. We're looking at a displacement graph. We're finding that no matter how I move around, backward or forward, in the end, after 4 seconds, I'm 16 feet away. We can do it a lot of ways. On average, though, that's 4 feet per second if you work it all out. Even though Jackson went backwards, his ball rolled backwards a couple times. That's okay. Now, to the next piece. Now, I'm going to deviate a little bit on this next section. So, are you ready to rock and roll? I'm going to turn the page.
Wait, what's the word after travel?
Traveled, distance traveled, that's an odometer reading. Your odometer as in how far you went. All right, telephones away, you 5 people that have them out. Let's talk limits. A limit, this is where limits are an essential part of calculus. We know a lot about limits. I'm actually going to revise. I'm going to go in and show you guys the things you know about limits right now. You want to remember there's a couple things. A limit is that L. The limit, let's do some that we know. Let's do our dirty dozen. You guys remember the dirty dozen?
Not really.
We're going to go find the Dirty Dozen. There it is. Okay. So
There it is.
now that it's back, even if you don't remember it, here you go. See if I can get it to clip.
What the heck?
I'm trying to make a screenshot. Don't make fun of me. Oh. Maybe? Oh, I can! Yay! So here's 1 over x. See that graph right there? 1 over x. Let's talk about its limits. Now, we did this Dirty Dozen once upon a time down here, and we talked about various, as x goes to this, to infinity, x goes to 0, and so on. We talked about where does the function go. Well, that was the beginning of limit notation. So I'm going to go back to that other screen, and if I can. I don't know if I can, but I'm going to try. If I can do escape while I'm touching this. Come on, buddy. There we go. Back in action. There. The limit, let's do it as x approaches various values of f of x is 1 over x. Okay? If you get sleepy, stand up and move around because, y'all, this is essential stuff. This is the f of x I'm going for. And I told you definitely wanted to have pieces of paper with you so that you could add to it. The note packet we have is, it'll be good practice.
Hey, can you close the blinds?
Hi. Yeah, she should have come down already.
Oh, she didn't go down.
Oh, cool. Thanks. Yeah, see you later. She wasn't supposed to leave after all. Okay, f of x equals 1 over x. Let's talk about this one. Here goes. These are all the things that we can do with 1 over x. There it is in all its glory. Once upon a time we said, all right, the limit as x approaches, let's go infinity. We talked about all the ends. The output of a limit is its height. So as we went to infinity, this graph went to a height of 0. So do you remember the output of a limit is its height, its y value. So output of a limit, keep that in mind, is a height. I think that's an often forgotten concept. So often, make sure you have a sense of it's just telling me how high it is as I approach these values. We also did limit as x goes to a negative infinity. So as we went to the left, negative infinity is also a height of 0. Output of the limit is its height. That's what you get. A limit gives you a height. So as x goes to negative infinity, f of x is 0, the height in there. Welcome back from your little vacation. Limit as x approaches, now we did all the ends, right? We did towards 0, but we did 0 from 2 different sides. It's different from the right. Remember the plus sign means from the right. That is the right-hand side limit of f of x. That would have been, as I come in from the right-hand side, towards 0 with my x values, where does my height of my function go? And this one keeps going up to infinity. And when we came from the left, it did something different. Now these are things we've done, but I wanted to bring it to the forefront of thy brain again. From the left, as you approach 0, you got negative infinity. Okay? Those are the idea of a limit is approaching a certain number without actually touching it. It says gets arbitrarily close to a but not equal to a is really important. Now we're going to play. We're going to do some serious stuff. This is where I'm going to go and get a new page, and I'm going to start a new set of notes here. You ready? So, right up here. Definition, informal limit at a.
Where the arrow is, where it's circled.
That's an L.
On the right.
On the right. Output of a limit is its height. Output of a limit is its height. And you guys can mess your desks around, get yourself turned around, come sit on the floor if you want. Have some fun. I'm gonna stop.